Good. So we began with some sort of motivation about cognition in the wild. I emphasized that a lot of cognition takes place when we do things like soccer. The next slide. So that things that we, often you think about high-level things like problem solving and language and mathematics as cognition, but soccer playing is also very cognitive, and pretty much everything that matters in cognition shows up in such activities. That was the argument I was making. For instance, planning, decisions, goal orientation, that perception for a purpose, so actively using memory for a purpose, using working memory, learning. The only thing that's motor is there is motor control, of course, then. And background knowledge is the famous problem of artificial intelligence. Background knowledge plays a big role, not just the rules of soccer, but knowing about environments and about properties of the world and things like that. So that's an argument that's been often done. And some people say, well, that's where cognition comes from, because in evolution, we developed cognitions as animals who hunted and communicated and so on, not doing math tests. And then the special point of view that we have in our dynamical field theory fold is that the significance about that origin of cognition is that the properties of sensory motor processes matter for cognition. So these properties are that you have continuous time, everything involves continuous in time, so that understanding how events happen, the computation events people often think about like a decision or in a sequence, the next step, that actually emerges from continuous time. And a thing like soccer, it's clear that emerges not, on a grid of decision times. It happens when get close enough to the ball, and then you have to make a decision whether to hit the ball in one way or another, or do something else. And these kind of processes are all characterized by graded state. That is, can do continuously many things. It's not all categorical. And you can link these processes to the sensory motor input any time, and or at any time. It doesn't have to be continuously linked, but anytime you can link it. And so that the issue of discrete events and categorical behavior must be embedded in something like that. And the last very important point is it happens in closed loop. That is, the consequences of your actions are influencing downstream actions through the world, because the ball is at a new place because you shot it, or your eye moved through the environment because of your action, and therefore you get different sensory input. And that actually theoretically really means that all of these processes in the sensory motor domain must have stability properties, and we made a big fuss about that. And the tutorials on dynamic systems, really the core concept around those is stability, and then the loss of stability, which is instability. And that's very clear in the motor domain. And then our hypothesis is that cognition inherits these properties. That is, that cognitive properties also have the potential to be graded, continuous in time, to be linkable to sensory information, to have stability properties. That's sort of the core idea of our kind of approach to dynamical systems approach, or dynamical field theory. It does not mean, say that particular to the cognitive science students who are exposed a lot to embodiment ideas in action, and what's the third one? The extended mind. This kind of discourse that philosophers have sometimes thinks of embodiment as a more concrete commitment that all of cognition is somehow contains motor components, or is very much about actions in the world, or about actions when you're situated in the world. And this is subtly different, right? Because here it really is about the properties of cognitive processes, but you could have a perfectly cognitive process where you don't activate muscle systems, and you don't, let's say, visualize, where you really just think and do mental arithmetic. And then the idea would be that mental arithmetic uses processes that are like movement in these dynamical properties, but that don't activate the motor system, for instance. Anyway, so that's now, I think after you've listened to this course, you might look back at that and maybe now see little bit more concretely what it is that we mean by that. The Breitenberg, right? Main message of the Breitenberg is this emphasizing that there's this sensitivity to environment, so sensors, motors, the nervous system, linking those two in terms of internal variables, activation variables, while the body links them physically, and then the structural environment from which behavior emerges. And the main idea was that even in this sort of armchair analysis of how behavior emerges, what you really have in there is dynamics, rate of change of a variable over that variable. And attractors play a role here. The attractors are really what create the meaningful state. So that was very interesting. Inside, we call these behavioral dynamics because the variables are about the body in the environment. And this links to cybernetics and classical forms of system theory. And then when we go to neurodynamics, we're talking about the inner states, so states of the nervous system acting as a dynamical system, and attractor states creating the states that just mentally determine behavior. And that was, of course, what all that course was about. So Breitenberg, sometimes I asked something about Breitenberg because it's so easy and concrete. And it's a little very special case, and a lot of the things we later discuss aren't really about these vehicles in space. So it's really more a metaphorical example than a concrete model where we really believe that something like that actually happens in mammals, and it's much more complex in mammals. Maybe some insects behave like that. So then the neurodynamics was really, so I didn't put here slides into this about the dynamic systems tutorials, which we had 2, I believe, this year. We'll split them into 2 lectures and spend a lot of time on that. And it's relevant for the exam in the sense that one of the major goals was that you develop a conceptual understanding of these notions of dynamical systems. So what is a dynamical system? What's an attractor? What's stability? How can you plot the dynamics, the rate of change as a function of a variable, the initial condition determining the future, so the current state determining the future, time courses condensed into the initial condition and the dynamic law, the dynamics, the function, rate of change as a function of the state. That's the dynamic law. It's just the initial condition, dynamic law that encodes implicitly the whole time structure of the trajectories. That's sort of the mathematics, and that is easy to ask in an exam, and I really would like you to understand. And that I have no hesitation about that, because that is a very general set of concepts that will, and if you understand those well, you can make much more sense of economic processes, of psychological processes, of I don't know, engineering. So it really has into a lot of things. So it's very useful to have a good understanding of that. And then so in the course, of course, we then concretely use these concepts to talk about neural dynamics. I talked about activation. Actually, I had this neurophysics module, right, with the spiking and these neurons and so on. I promised not to ask any details about that. I'm not going to ask you about membrane potentials and so on. It's still useful to know these things, to know the basics of how the nervous system works. But I'm not going to ask you about Nernst equation or things like that. So I'm going to stick to neurodynamics. So in neurodynamics, we use these activation variables, and we said they are related to biophysical things in neurons, the membrane potential, spike rate, and so on, but it's not specified. It's an abstraction of those things. It's really ultimately defined by the sigmoid function that ultimately determines how something acts out in the world, determines behavior. In the last lecture in the year 2021, which was this video about how to control a robot, sort of illustrated the idea of how ultimately activation is translated into some motor behavior. But it's an abstract descriptions, like in connectionist descriptions and some of the models of mathematical psychology, like ACT-R and SOAR, some inner state variable that determines what effectively will be transmitted to downstream systems. And so the sigma is very central, that only activation that passes through this threshold function will be noted, will have an influence on other activation variables and ultimately on the motor system. So that is sort of the fundamental idea of connections as well, that it's the sigmoid that defines the scale of activation. Something that's large enough to switch the sigmoid to on is large, and something that's below that is small. That gives you the metric. And if you take different slopes of this function, it really just means that the ranges of values that are relevant are different. Horizontal. And then activation dynamics is explaining for continuous time courses. So this is the concrete form of the neurodynamics. So this is the thing I always ask, can you write down a neurodynamics for some activation variable, and that you understand it's the rate of change of activation as function of activation. And it has this always an attractor, because this is minus U term that comes ultimately biophysically from the membrane, from biophysics. You don't need to know how it arises there. You just need to know that is something that is true for all neurodynamics. And that is where neurodynamics is different from neural network thinking, where often neural networks are framed as output as a function of input, or sometimes as like an iterative equation where the next value depends on the previous value. But these formulations are sort of approximations true for some simplified networks like forward networks, or networks where you don't actually take the dynamics, the time courses very seriously. But when you do a biophysically more realistic version of such neural networks, they are neurodynamics. And then the minus U here, that makes the stability, that makes the attractor, that is something that is not contained in regular neural networks. They have only excitatory, so sigmoided inputs. There's no sigma on the minus U, right? It's a different term. So it's different from the inputs that could be positive or negative and that are transmitted. It is something that's intrinsic to the individual neurons or to the populations that we're looking at. So that's the opportunity to think about how attractors determine the flow. The ensemble of solutions is organized by the attractors. Exponential time courses are given here by the time scale tau. You can also divide by tau, and then it's minus 1 over tau. 1 over tau is then the rate of change, the slope of this function is 1 over tau. It has this reciprocal units of 1 per second, or if you put it here in front, it has units of second. And that is this exponential decay time scale. That's a good thing to talk about in the exam. And so inputs are other terms in the equation other than the minus U terms that don't change their sign. They are either positive. They can go from 0 to positive values or from 0 to negative values. In the first case, they are called excitatory. In the second case, they are called inhibitory. And so they are contributions to the rate of change, not direct contributions to activation. You can see that what happens in the input-output picture is that you assume that the dynamics is so fast that it has already gone to the attractor. So then the attractor would mean U dot is equal to 0. So you have a 0 here, put the minus U to the left side, and then you have U equals the inputs, right? Then that will be an input-output system. And that approximation only works when there is no other U dependency on the right-hand side, right? This is the only U dependency you can quickly solve for that attractor. If you have other terms there, then it's no longer obvious that the inputs determine uniquely the output. And in fact, not always true. So if in the neural dynamic pictures, inputs sort of shift this minus U curve up and down, up for excitatory, down for inhibitory. And then you can see that if you do that, the attractor shifts along the horizontal as a result. So when you shift the dynamics up, then the attractor moves to the right into the positive regime where the neuron can transmit its activation to downstream systems through the sigmoid, right? So this is also something I often ask people to show that they understand that logic. And why is the resting state negative? Well, relative to sigmoid and so on. And then we have these two cases, self-excitation and competition. So self-excitation is really just involves one neuron, but it's a neural network in the sense there are more than one input. So it's really just one other term that now does depend on you. So it's a recurrent neural network. That's where this input-output picture doesn't work, because you need to know the output to compute the input, right? And the neural dynamics is really the very natural picture. And then it's this idea that it has the -u term that is shifted by some constant in the positive half space. That constant, when u is large enough, it's that level, no? That constant that it shifted. And there's a transition region here where it's nonlinear, and that gives rise to these instabilities, right? The detection instability and the reverse detection instability, and these are things I very often like to ask, that really understand those, not just go through the motions, but really understand what the logic is. And interesting, the detection instability is really the instability of the off state, right? Of the not where you haven't detected yet, and that becomes unstable, and that you have another state, a variable for that, is a property of the sigma. So that is sort of a separate issue. And the reverse detection is when you lose that other state, the self-excited state. And then these two neurons with mutual inhibition. Again, remember this case here, you can have multiple neurons that are all excitatory, and they can also excite each other. Qualitatively, it will always have that kind of behavior. So this is not just easily translates into populations of neurons. And so this brings in a new quality in this picture, because now we have two neurons, which again could stand for a whole set of neurons. Two neurons that are mutually inhibitory, where this point here indicates a negative coupling here, inhibitory coupling. And so neuron number 2 influences neuron number 1 negatively, and vice versa. And then new things come about, essentially selection decisions, right? And I explained that in this vector field case. It's only in 2 dimensions that we can really usefully talk about that. In the vector field picture, we can understand that there are 2 possible attractors where neuron 2 wins or neuron 1 wins, here visible from the fact that you're in the positive half space for that neuron. So for instance, for neuron 1, you're in the positive half space. For neuron 2, you're in the negative half space. So in the positive space, it transmits through sigma its activation, right? And before that input is applied, you're sitting really here in the resting state. So you can easily read off the boundary of the basins of attraction, whether you're going to go to this state or to the other state. So that is something I think it's good to conceptually understand. I don't think I'll be asking you about vector fields per se, because this is a bit more just mathematical. And in most of our work, we don't really think like this. It's just an illustration, right? It's not so important for our practical work. And so then we went from 2 neurons to continuously many neurons in the neural fields. And that made sense because of how we think the connectivities from the sensor systems to the motor systems arise, and how, or from the neurons to the motor systems. And so if you have these discrete neurons, always question, what do these neurons stand for? Neuron number 1, what does this stand for? You have some connections models where people say, well, this is the neuron that stands for phones, and this is the neuron that stands for headphones. And then say when the phone is visible, then that neuron gets input, and so on. But these are sort of metaphorical ways of speaking, because it's actually not clear how you go from the retinal image to a particular neuron being activated. That's an object recognition, detection, maybe even a segmentation and localization problem of knowing, there in the visual array, that thing is the phone. It's much more complicated than saying a particular neuron gets input. It would be the thought that the whole hierarchy from the sensory surface to that neuron made it come on, but you see that's pretty complex for a case like this. So these are more metaphorical models, and often operate with discrete neurons that are labeled standing for this. They call that labeled line, that this neuron stands for this and that neuron stands for something else, like a neuron that stands for the letter A and a neuron that stands for the letter B. But that's not very embodied, right? There you're not really taking the link to the sensory surface seriously. So when you take it seriously, you have to say how come that a neuron stands for something, and that comes about by it having connectivity to the sensory surfaces in some way. Here, of course, also very simplified that somehow there is a mapping which is one-to-one, but usually it's much more complex, maybe feature extraction or even categorization. And then neurons here will be activated when there's a certain kind of sensory situation. And it's that connectivity that determines how, what is being represented. We looked at cases where these are dimensions, feature dimensions. Very often it's just visual space, retinal space, or body space, or it could be simple features. But there are actually more advanced models, and we only gave you a little hint at that, where the transformation from the sensory surface to these fields is much more complex. And analogously, if you have some representation of activation in a motor system, it becomes, it obtains its meaning from how it is connected to the motor system. And I argued that the motor system always actually involves some kind of behavioral dynamics, some kind of dynamical system, which we made explicit in this robotic example. And the muscles are dynamic systems through the reflex loops that have, but also physically, they are dynamic systems. They have attractor states, and these attractor states are then the behaviors that arise or explain the behaviors that arise. There's more to that than I cover in this lecture. In the summer semester, I'm talking about that a lot more. So that effectively, this I didn't really say so much, but these spaces that are represented are in the perceptual case spaces of possible percepts, and in the motor spaces of possible movements. But this is a bit misleading because it actually is also about attention, about selecting a single element here or a small number of elements. Well, you could think of possible percepts as being images, so they're very complex. And the feature-based theory of perception is actually that's not what is neurally represented in your brain. Neurally represented are objects that you attend to through their feature values. So you see there's something round, white, and that is a phone or some kind of packaging. And that's what you perceive. You perceive these properties, and then you look at some other object, and you have an impression that they're all lined up there. But to give answers to questions about your visual environment, you actually have to bring into attentional foreground the individual objects. I can tell you that now I have a very personal, intuitive experience for that feature-based property of perception, because my right eye has this damage, and the retina is not flat and homogeneous anymore. And so the image that I received through my right eye is sort of like a photo that you would crumble a little bit. So it's not straight and unstraight. It's sort of a little, get some funny texture, and it's distorted. And when I fuse the two images, sometimes I can do that and see an object, then the object has, some places has this kind of wrinkled characteristic. It's like the features represented coming from my right eye, they contribute to that. If I actually move an object across an occluder so that the left eye sometimes is occluded and sometimes the right eye, I can see how the object switches from being smooth to being wrinkled. And I can see the contributions of the two eyes. And so there you get a good sense that it's certain, it's the object is represented as a feature bundle, as technically some people say. It is spatially laid out, but the properties are represented as feature properties. So it's not like a little image is in your mind, right? That's not right. And that's how you can understand these peaks. It's just a single peak and a single feature motion direction. It's in reality a vector of many feature directions, but that is the idea of how the population in the brain represent percept. So hopefully you can bridge that gap from these very trivialized cases to more complex cases. So sidesteps this whole idea of having an image in your mind. There is no image there. Yeah, we skipped this neural implementation. I think Sophie talked about that in one of the discussion sessions, and I gave you slides, so I'll not ask you about that. Yeah, and then of course critical is the dynamics of neural fields. So that's also a big topic for the exam, to talk about this. Maybe even this equation. I think it's very fun if you try to understand this equation, even though it has funny integral, a little difficult to understand, perhaps the exact mechanism of the convolution. I don't want to force you to understand that, but intuitively to understand that the dynamics is the evolution of the whole field of activation. Time and again in the exam, I ask people to plot a field, and then they, instead of a field, they plot u dot over u, or they plot something over time. And so to understand that u can depend on x, but also on time, and it depends on x, that x is like the index, continuously many activation variables. And plotting the state of the field is like giving one value of activation for every value x. It's a different thing from plotting how activation evolves in time, u of t. And that's different from plotting u dot versus u, which is plotting the dynamics. And for fields, of course, we can't do that because it would be infinitely many axes here and infinitely many axes there, right? You can't really plot that, so we never do that. Yeah, and so this local excitation, global inhibition, as the support for selection. This is the example I'm showing in this little automated simulation. So we went through all of that. We looked at peaks as these attractor states, detections, instability, selection, and working memory or sustained activation. This picture here, and I think all of those you should have some understanding of. Not very technical, but intuitively maybe say what is a peak, what is upper threshold, what does selection mean? Can there be multi-stability in selection? Where's the limit of stability of that? Do you have sustained activation? Yes or no? Memory instability as the limit between those two. The boost-driven detection instability might be useful to look at that again. And then we went through examples. So that's really the concepts. I would say that that's the stuff that you really should understand up to here. The rest were more exemplary examples, and I could ask general points about those examples. I'm not always asking to remember all these examples by heart. So we argue generally that the detection stability is important to stabilize decisions, I mean detection decisions, whether there is something of the nature, whatever the field represents. And the argument is that, if you create a stable state, then the transient to that stable state is a clear event. So even if the input after you've moved there weakens, you can still stay in that state, so you don't depend on the input so strongly. And hysteresis would be the technical way of seeing that. I gave some examples of hysteresis. But for you to understand what that means, hysteresis might be very useful. It's also a very general point. This is something that happens at many levels. People have decision hysteresis also in much more cognitive tasks, like, you always buy a, certain kind of product, for instance. It's actually a little bit metaphorical in that case because it's really more a learning process. The selection instabilities, again, stabilizing selection decisions, that was the argument. And so rather than look at any time at just who's the maximum, you say, I'm committing to a decision. And now even if the bias toward the one choice becomes weaker, you stay with that decision until you reach a limit. That will be the selection stability. And we took, remember, eye movements, and I'm not showing that here, the eye movements as an example, where you make free selections, and later we had the A0B experiment, babies selecting one of two objects, something they do without the explicit instruction which one they are supposed to go to, while most experiments on sensory motor decision-making are in this reaction time paradigm where you are told what the right choice is through an imperative or go signal. So an imperative signal tells you what to do and also tells you when to do it. And the time between that signal and the response reaction time is used to measure how difficult the choice is, the computation is, as people classically say. And in dynamic field theory, it's really a measure of how different the initial activation pattern from the final activation pattern is, in the sense that when it's far further removed in some metric sense, then it takes longer to get there. And that led to this paradoxical effect that when you have choices that are closer to each other under some circumstances, you might arrive at the peak that, at the right choice faster than if they are further from each other, really because, essentially if you're selecting this one here, then, this activation is already a little bit higher. So it's closer to the full peak that will develop, not by much, but a little bit than this one. And so it's magically closer to the final state, which is counterintuitive because people often think of that as a computational task, where the computation, when these are closer to each other, you have to compute the different, let's say you have to compute the correct movement direction, you have to compute it to more precision, so have more information, more digits in a numerical representation than if they are further apart, to find a value that is close enough to the choice. And so there one would predict the opposite, and we also discussed the relationship between that. I also mentioned the Higgs effect and other effects, but I don't think you have to remember all that. If you understand that concept, that it's a question of the task set. So how far is the representation that you have here from the representation that you have here? And that determines how fast that transition is, and far in a function space, right? This distribution. And then the time of an initiation paradigm is actually a way to directly observe those distributions. So this paradigm where you're training people to make the response at a time, and therefore you can control how much before that time you give information about you give the imperative stimulus, give information about what to do. And there you can actually observe, when you repeat that many times, you can observe the probability distribution of their choices, for instance, bimodal here, when the metrics are close, are a certain distance, and monomodal when they're closer, and actually also in time, early time monomodal and late in time bimodal. So that is a way of directly observing these distributions here at probability distributions, but reflecting hypothetically neural distributions in this little neural grounding model we showed. You can actually really sometimes observe these as neural distributions, and therefore you can directly see this metric distance. So here, for instance, I dropped the theory figure, but remember there is a theory figure where you can see how for certain choices the difference between the initial distribution and the final distribution is larger than for others, and that affects, for instance, your precision. Yeah, and that's the three instabilities: detection, selection, memory. And then we talked about the memory trace briefly. I think in this year, I didn't expand that very much. It's sort of the simplest learning rule, simpler than Hebbian learning. And that's a way to reflect the history of activation. So ultimately it leads to a distribution in the memory trace that reflects where and for long peaks formed. So and the memory trace is somewhat specific to our approach. I think it would be good if you have some conceptual understanding of it. The equation is really somewhat, we invented that, so it's not something that I would say is written in stone. I did have a whole complicated lecture, I would say, about working memory, and that is quite advanced, and I'm not asking you to understand everything about, especially this 3-layer model. I think I have a slide about that here. I think that's something that is to illustrate how complicated it can get, but I don't think that I will ask you anything details about that. So it's the notion that working memory is sustained activation, as we had earlier, and then you find actually interesting things in the literature that it's really about space, about having different objects that are spatially separate. And it for the capacity, so how many objects can you keep in mind like that? Only about 4, plus minus, maybe 5. It turns out it's more 5, and because of the encoding, decoding things, there's a little bit, still a certain probability of error when you have 5. And so not 100, unlike you might imagine. In work memory, we have very limited capacity, and it depends really on these number of objects. So for instance, when the objects are complex and they have multiple features, then remembering these objects can mean that you have to know 15 or 20 pieces of information in the sense of knowing, what was the color inside and color outside, which shape did they have, which orientation, and so on. But they were in 4 objects, in 4 locations, and then so the constant is this 4 locations, but you can have variable amounts of information associated with each object, which can be easily understood in this theory that I only hinted at binding through space, that capacity is limited by the individual fields that are over space, and then you can collect multiple such fields into a bound object, a particular location. And so the capacity limit is very natural in the fields, because if you have inhibitory interaction, the more peaks you enter, the more inhibition. At some point, there is so much inhibition that no new peaks can be formed. So it's not that the number 4 is special, but that's an empirical observation, but that there is a capacity limit that's linked to space is important. So it's measured through this change detection paradigm. So you don't remember. So if I ask you to list all of those things, then you will perhaps have a hard time to describe from memory these objects. But what we're really asking you is to look at an array like that and then say whether after a break, if the new array is same or different as the original array. And sometimes you can ask people to point out where the difference lies. And it's under those conditions that you have that capacity limit, that is just a question of the number of objects. And so we made a model of that, this 3-layer model that is sort of a universal circuit in the brain. Well, I didn't go very deep into that, and I don't think you really need to understand that. But maybe you register that by making more complex layered models of these multiple fields, you can have sort of uniform computational units that will be present in pretty much any cortical system. There is actually a hypothesis is that these are sort of universal little computing machines that can do detection, selection, working memory, entry, so sort of detecting that there's a match, that you enter something into working memory, and also deletion, which I didn't talk about, how to get rid of a working memory. The example where all these instabilities are combined is the A0B experiment, and I explained that only in the context, I believe, of the robot, if I remember correctly. Or I did it in the memory lecture, I think, yeah, where all these things play a role. So this picture where you select A and then this is the picture of spontaneous error, and other pictures are with the A0B error where you stay here. It'd be good if you understand A0B, I think that's a very good example also to bring it all together, right? All these different instabilities. A0B has some subtleties. Actually, there are some things that are a bit fuzzy about that. Feel free to be confused about it. Well, it's just talking intelligently about this would be a very good feature in the exam. So then finally, there was this lecture that I only gave by video, where we talked about behavioral dynamics, a vehicle. And I'm not going to ask you about this vehicle dynamics. This is the topic of the summer semester. And there was this critical issue of how a peak is translated into a dynamics. This is an abstract conceptual point. I'm not going to ask you about that. It's abstract, because in reality, when you're not a vehicle, there is actually more here. There's some muscles and reflexes and time generation and so on. So this is only an idealization. Yeah, this example is useful to understand the inputs, how the peaks come about, how the detection, selection, memory really deliver function, and then it has this very simple tie to action. So from then on, that was like the new year until now, where unfortunately it was all videos, and then Sophie gave you this excellent CEDA workshop, which only some of you already participated in. So that is, none of that is something that you have to know in a technical sense. I think it would be still very useful for you to understand the notion of high dimensional fields. And high dimension, again, is not about the number of axes here, like retinal space is 2-dimensional versus 1-dimensional. That's not what we're talking about. There's no problem with that. It's that when they have different qualities, like this one is color and this is retina, that then interesting things come about. And the most important one is visual search, is this capacity to specify something along one dimension, like here, color, make a slice, so activate a whole layer of the field, maybe with in 1 dimension will be a ridge, and in 4 dimensions it's a whole cube in a four-dimensional space. And that combined with the actual high-dimensional information that comes from your forward feature extraction, where you know which color is where, you can then search for something that has that desired color, like the color green, which would be this object. So that's this notion of visual search. I can extract the green object by introducing that slice. I'm not sure that was the exact illustration we used, but that's certainly useful. I think we might have used this one here. And then we talked with the operations of bringing in binding and unbinding. So you can say in this field, color and space are bound because every field is a particular combination of these two values. So they are bound to each other, but they are bound in a fixed way because they are anatomically bound. But operationally, you can bind them if you have the separate information. You only know the color and the space. You can induce the bound representation by these ridges, and you can also extract that. And then coordinate transforms emerge from that. In coordinate transforms, you bind a particular representation, like a retinal one, with the transformation parameter here, the gaze direction. So any combination of these two variables, so any combination of gaze direction and retinal position are represented here, and you can project out from that then the transformed representation. So for instance, along the diagonal, that is a representation that is body-centered, but you could compute some other reference frame from that as well by projecting out other functions. Yeah, and then this was also just a video, relational thinking. That's just an illustration of the use of those things. So a case where you can remember the grounding of a scene, and grounding, perceptual grounding of that scene really means that you know what that person is talking about. Red to the left green, you know that person is talking about that red, and it's this green that this is to the left of. So that simple act of, it's also called the targeting problem, or sometimes the reference problem of knowing what that sentence is about. That's it's not as simple as semantics, and semantics is actually about you knowing what red means and what the relationship means and so on. This is really referencing, knowing how to relate your perceptual experience to that language. We call that perceptual grounding, but there are different terms for that. And that is sort of a entry point, an embodiment entry point into higher cognition. And I thought that was quite interesting. The interesting about that architecture is that it has all these elements that you were then familiar with. It has the coordinates forms, it has visual search kind of things up here, it has these discrete nodes and sequence generation here, which we only got later. And yeah, these concept nodes are maybe new. And that was a show and tell story. So you don't need to really know that. Show and tell that these systems can do hypothesis testing. So they can bring up a hypothesis like that the reference object is here, this green one, but there's nothing to the left of it. So you can actually ultimately suppress it and switch to the correct hypothesis that this is the reference object and that's your target. Yeah. Reference object. And then the target comes up here on the left. Yeah. And the last video you saw, which was also two pieces of the video, is about how sequences are organized. It's something that's very general, that our current work is very much around that, the thing we call condition of satisfaction. Sophie is just making a major step in that direction. And it's a very general idea that any representation is paired with a representation of its condition of satisfaction. So what logically determines whether what you have represented here is the case in the world. So in motor kind of activities, that will be the intention, will be a motor intention. And you're representing whether that motor act was successfully completed. And that's the example that was shown in that lecture. Turns out that you can also think about perception this way. In perception, the condition of satisfaction is actually the same as the intention. So the fact that you have that the detection decision means that the input match something that is possible inside your system, and it's by that matching of the synaptic pattern, the feature extraction, that does that. Again, this is not something that you need to know. think we showed you that example of serial order as being built in that way. Okay, so what did you learn in this course? Hopefully, just in time. This course was a little bit different because a lot of the skills were general, right? You had to read some papers. You had to write. The exercise with this writing of technical stuff. We had one or two where you had to do some mathematical computation, but most of it was just writing in a mathematically precise form with illustrations, labeling the axis, knowing what you're doing. And I think that's a much underrated skill that is a large part of your practice as a trained university degree holder, and depending on your field, as a trained engineer or computer scientist or cognitive scientist, a lot of it will be about that. So that's something that we trained a lot. And you did this essay, which was sort of the high point of that, right? And the essay actually summarized really pretty much the core concepts until we got into the New Year lectures. And so that's very convenient because that's really what you need for the exam. The mathematical skills were really, again, not really skills in the sense of being able to do computations yourself, really understand the concepts of dynamical systems, maybe to not be shocked when you look at a differential equation, to develop a way of looking at them and understanding what they mean, what these terms mean, even for simple cases, kind of predict the solution, right? Rather than solve it analytically or on the computer, you sort of mentally expect what happens, essentially, for these attractor kind of equations, because then you can say, well, it will move to the attractor, and whether or not depends on how close it is. Is it in the basin of attraction? So these sort of ideas, I think you can really have learned. And maybe to have some understanding that one can solve equations numerically, and when you do that, you're doing experiments. That is, you're trying different things, different parameter values, different initial conditions, and so on. And that means you have an experimental paradigm where you're asking questions about the property of that model. So you're doing experiments with the model. That's why numerical simulation is different from just solving the equations in general. And then I think that one of the core skills taught in this course is to deal with interdisciplinarity. I don't think there was anyone here who was familiar with all aspects, even cognitive science, which is a very interdisciplinary field itself. Even if you train that in that field, you likely did not know all the concepts. You might not have had the mathematics, or you don't know the robotics, or you don't know the neuroscience or some of the psychology. And so dealing with concepts from different disciplines is a skill that's very much in demand, that in a lot of professions you do all the time. When people talk about computer scientists, especially in applied computer science, as a programmer, most of the time you are talking to people who are not in your field, who are in the business side of things, or engineering, or marketing, or whatever it is, and or human factors, and then you need to communicate well with these, and this means that you have to handle well the extent to which you understand the concept of the others, deal with things that you don't understand, that somebody's got to be responsible for that, and somebody has to explain that to you, or you just keep a note that this is something I don't fully understand. So it's very good as a sense of sharpening your metacognitions, or sharpening the sense of what you understand, what you don't understand. That's a very personal issue for me too. I really hate the school-like atmosphere that sometimes happens also at the university, where people just say things because they know that's the sort of thing you have to say. The teacher expects you to say that, right? There's something very bad in the exam. You really want to never say anything that you don't know what it is supposed to mean. You just know it's a phrase that people say, right? That's not knowledge, it's anti-knowledge, because you don't even know that it's wrong, right? That's not what you want. So I think that this interdisciplinary context really sharpens that, because in the interdisciplinary concept, there will be sometimes things that you can't fully understand, and what is important is that you know that, right? And that you still have a way to handle it, and for instance, delegate that, or say, according to that field, this is so, but I don't know exactly why. It's even ultimately a question of character. Hopefully this was also fun. Some of the discussions we had were fun. That was also a goal, to make it enjoyable.